He's in charge of both the Space Shuttle and the International Space Station. This year is not only the 50th anniversary of space, but the 30th anniversary of Bill working for NASA. And he began working on the space station program some 17 years ago. Then he headed the Space Shuttle program at the Johnson Space Center, then later the Space Station program at Johnson Space Center. And he did so well flying these two vehicles that they appointed him to fly a desk in Washington now and to run both of these programs. So he's what we call the engineer's engineer, and I think you will really appreciate what he has to say about the challenge of evaluating risk during a space flight. Bill?
Thank you, John David. It's my pleasure to be here today. I know it's kind of early for some of you, but there's a pretty good crowd, and hopefully I'll try to give you some information, some things that you don't hear on the news, but some things that you can use and put into practice as we go about this business of spaceflight that we're all in. I'm going to talk to you a little bit about STS-118. That's the last shuttle flight we just flew. I'm going to give you some insight into the analysis that went behind the tile damage that we had on the shuttle. I'll also give you some insight into the decision process we went through to determine that we didn't need to make a repair on the bottom of the shuttle. And I do that for you because our business a lot of times involves a risk versus risk decision. And I think it's good that you hear the non-media presentation. You hear it from kind of the agency. You hear it from what we were really looking at. I'll try to present the data as openly and clearly as I can. So then it'll give you a unique insight into the logic, the rationale behind our decision making and our thought process, and hopefully you can use that in your jobs and you can apply that in the space community in general. So with that, we'll start with the first slide. I won't read all this to you, but this is what the mission was really supposed to do. And they accomplished everything on this mission. We had the educator astronaut there. We activated the power transfer system on board station. That takes the power from the solar arrays on space station and provides it to the space shuttle. That was the first time that system was ever used in space. It required us to modify the space station. We actually had to string wires on the outside of space station to use that system. We had to modify the shuttles as well and put power converters on board the shuttle to receive that power. It wasn't for certain that all this would work because the hardware had never seen each other before, had never interfaced, but it worked smoothly with absolutely no problem. So that's a real tribute to the team that we can design, put things together, never see them operate together, and then operate them for the first time in space, and it was fully effective. And you don't normally hear those kind of stories. I think the other thing we delivered was a little small truss segment, the S5. That's important. That was done fine. We used the space hab to transfer up a lot of cargo, a lot of experiments, and overall the mission was 100% success. But the kind of the story that you hear in the media is really about the tile damage. One of the things that we've done since return to flight is, as the shuttle approaches the space station, we do what we call a rendezvous pitch maneuver. And in NASA words, we always make things acronyms, so an acronym is RPM. What we do is we essentially auto-program the autopilot for the shuttle to do a flip maneuver. And while they do that, the crew on board space station pulls out their 800mm lens and takes pictures of the shuttle so we can get an image of all the areas on the shuttle. When we did this maneuver, this is the picture we got down from the crew. There's a damage site there that you can see. This is the actual picture that was downlinked to the ground. So we knew we had some damage in the tile area, and that's on the bottom of the shuttle. That's just behind the main gear and just a little bit upstream of the external tank door. And you can see the dimensions. We were able to scale from that about roughly a 3 by 2 inch kind of damage on the shuttle. But this is the kind of resolution that we get from the cameras on board space station. When we take that data, we look at it on the ground and we determine this is an area we needed to look at closer. So we pull out the robotic arm on the shuttle, and we were able to go ahead and do a detailed focused inspection. And then this is the picture we get from that camera that sits out on a boom. So we actually fly an extra boom up in addition to the SSRMS. We attach that to the bottom or to the other arm. We then go underneath the orbiter with this camera suite, and we get images like this. So that from that crude picture you saw from the crew, this is the image here. The other thing that we get that's really unique is we have a laser system that actually scans this defect, and we store all the points in a CAD-CAM program, and we have a three-dimensional map of the actual damage underneath the orbiter. So we knew with precision exactly what the damage was. We had a numerical model of it. We have a three-dimensional damage model. And then the question is, do we need to try to repair this, or is this okay to come home? And you'll see that little area down there in the bottom, that little dark region. Between the tiles sits a strain isolation pad. It's essentially roughly a 16th inch piece of Nomex filler that sits in there, and that was exposed in this case. So in this case, we actually had total tile loss in a very small area, about 1 inch by roughly about 1/4 of an inch. And we knew we had total tile loss in that area, and the question was, is that acceptable to come home from a thermal standpoint, or is this something that we need to go underneath the vehicle and repair? The other thing that we got on this flight is, like all our flights now, we have a lot of imagery. So we use cameras from the solid rocket motors to take a look at where the damage comes from. So we knew exactly where this piece of foam came from that hit the bottom of the orbiter. You can see the ground imagery on the top left-hand picture. This is a 17-inch line that liquid oxygen flows through to the shuttle. You can see what it looked like prior to flight. Again, in the top images, and down in the bottom you can see what it looked like pre-launch, then 57 seconds after flight, and then at 58 seconds after flight. And what you can see is we know exactly when in time that piece of foam was liberated. We know that piece came off at a certain velocity. We can actually track it in the images. So we now have another key piece of data that helps us build the model. We know the physical damage we see underneath the bottom of the orbiter. We know what piece of debris was liberated. We know the approximate mass of that debris, and we know the velocity of that debris. So we can then analytically assess whether there are any structural damage beyond what we can see visually. So again, we use all our tools. We use all the analysis and pictures from ascent along with the analysis on orbit. Again, this is another picture. This actually captures the debris in flight. It came from this upstream location, station 1623. It went back. It hit an external tank attached strut. It ricocheted off of that tank strut and went straight up into the bottom of the orbiter. So in a sense, this is a fairly remote or fairly unlikely event in the fact that this debris had to transit back, directly hit the strut, and then come off the strut in such a direction that it could actually damage the bottom of the orbiter. So we don't think this is a high probability event. That's why we didn't see it in our models. We knew we potentially could lose foam from this area, but we didn't think that we would have much of a chance of getting to hit the orbiter. We've now run some analysis, and it turns out it's still a pretty low probability event, but it took the fact that the piece of debris actually had to come off, go back, hit another piece of structure, and then hit the orbiter. This next picture shows the actual videos, a screen capture of that. So again, the video system that we flew since return to flight allowed us to see the foam come off. It allowed us to see us come back and see it hit the strut, and it allowed us to see us go from the strut back up to the bottom of the orbiter. So again, we put in place a very logical system to get us all the data to make sure that we're really safe to fly and safe to return when it comes time to make the decision to come home. This is an actual image that comes from the computer system. This is this 3D model that I talked to you about. We actually have a point cloud of data that sits there that describes totally this defect. And what we were able to do is we were able to actually take this point cloud, put it in a numerical control machine, actually put some tile underneath the numerical control machine, and actually machine the defect in tile on the ground. So we had the exact failure mimicked on the ground because of a numerical control machine that mimicked this. We made multiple copies of it. We were able to then take it, and I'll show you in a minute, into the ArcJet, actually run it in the ArcJet wind tunnel to confirm it would be safe to fly. So again, we've taken this ability to look at damage in space, turn it into a series of geometric points, download those to the ground, turn those points through a numerical control machine into a piece of tile that mimics exactly what we have on orbit. So we've really been able to really improve our understanding of the problem that we had. Now this is the aerodynamics, and so the aerodynamicists in this room will love this. We didn't really have the ability to analyze the actual damage, and the actual damage is the large section down in the bottom. As you notice, it had essentially two steps. It had one step down in the bottom where it was deep and the filler bar was exposed. Then there was another step where it came back up and it had a very high, or very steep back wall on the tile. And so our mathematical models can't handle this two-step problem. So we simplified the analysis to be the pictures you see up on top. So essentially we had just a nice generic slope ramp down on the front and then a very nice generic slope ramp up on the back. And then what we did was we wanted to analyze it two ways. We weren't sure if this filler bar material or the strain isolation pad was present or not. That's that brown area that sits there on the picture on the left. And then on the picture on the right, we assumed that that was gone. So we wanted to analyze it in a worst-case scenario. So we said, okay, there's no material. Let's assume there's no material down in that bottom of the damage slot at all. There's nothing there at all. The aluminum will be exposed to the heat of reentry. Can we tolerate that from an analysis standpoint? Can we tolerate that from a return standpoint? Or do we need to do something and go out and repair it? So we essentially analyzed, I would say, a nominal condition and then also a worst-case condition. Yeah, maybe a pointer would be great. You can hardly see it up there, but this is the nominal condition with the material present in the bottom. And then over here, there's no material in the bottom, and that's the aluminum substrate exposed. The other thing is we knew exactly where it was on the orbiter, and we were lucky in the sense that there was a large structural aluminum member right underneath this area. So that was a very nice heat sink, so that if any heat transferred into that aluminum structure, it would be essentially taken away very quickly into the spar that sat right underneath this damage location. So that was another key piece of data. The other thing you'll look at is in this picture, you can see how the flow tends to get neck down or gets pulled down into this area, then comes up and then circulates around. There's a high heating area back here where the tile gets exposed. Essentially, you can think of the airflow hitting it here and stagnating and causes a high heating zone here. But that's mitigated a little bit by the fact that there's this cavity down here and it tends to pull the streamlines down and soften some of that flow hitting the wall. And that came into our decision of if we were going to repair this. You know, if we were going to repair it, we were concerned that if we just we have some putty on board or some material we can put in here, we could have filled this bottom part in, but we were afraid that that might have actually made the situation worse, because instead of the streamline getting pulled down in and then softened as it hits this back wall, it would have probably actually increased the heat transfer on this back wall and made a very local hot spot here. So if we were going to repair, we needed to have an assurity of the repair that we could fill this entire cavity in and not just partially fill it. And that was kind of that's another key piece of data was we didn't have, we knew the repair technique could make things different, but we didn't know it could really repair. And the media has a real trouble with that concept. When we say repair as engineers, you know, we're making it better, we're doing our best techniques to improve the situation. When normal folks hear repair, they think it's fixed, it's no longer a problem, it's perfect. In this case, we could never return this condition back to perfection. We were stuck in some intermediate condition where we took the tools, the techniques we had, we could make it different, but we couldn't necessarily make it any better. And that was the dilemma that we faced, and that was the dilemma that we had to try to explain to folks. And that's the crux of the risk versus risk decision. That to folks on the street, why don't you just fix this and go put goo in here and seal it up and make it look perfect and it'll be fine. But for us, our techniques would help in a catastrophic condition where we had to do something, but they couldn't help in this condition, and it could actually make things worse. Again, this picture is the unit, piece of tile that we actually had on the ground on the upper left-hand corner. So we actually, as I described to you, we were able actually to machine that exact defect in a set of tile. And then down in the bottom is we ran essentially an arc jet run or a wind tunnel test of this actual condition. Based on the aerodynamic analysis, we assumed a worst-case transition at Mach 17. And when we do that, This is the results we got from the wind tunnel. And what you see in the wind tunnel here is you see a tunneling effect. And what happens here is our tiles are made of silica, which are essentially just sand particles that are separated by a lot of air. And what happens is when this flow stagnates on this back wall, it glassifies and makes a very dense glass-like material. That then has, since it doesn't have all the air in it, has very high heat conduction. So then it tends to conduct the heat right back in, and it runs or it tunnels back through the tile. So we knew that this could happen, but from an overall worst-case standpoint, this was totally acceptable. There was be no damage to the shuttle underneath. We might have to repair a little thing underneath, but probably not likely. So this was kind of the absolute worst-case condition that we could end up with after return. So we knew there was no risk of loss of the orbiter, there was no risk of loss to the crew. We knew with certainty that the worst case we could have some kind of phenomena like this, and our concern was if we repaired, we might fill this area in and almost ensure we get this kind of running and tunneling effect. So based on that analysis and that data, and again, I can't stress how difficult it was for the teams. There were 5 days, 5 24-hour periods where all we did was aerodynamic and thermodynamic computer runs in 3 facilities throughout the U.S. So we understood this failure better than any failure we could have had. And again, that factored into our logic and our decision process. We knew this failure was not a problem to return with. We knew it was okay to come home with. But if we tried to repair and we didn't affect a good repair, we are now in another unknown condition that would have taken us another 5 days at least to analyze, to figure out what the heck we got. So we knew the condition we were in. We knew it was safe to return. It was the right thing to do to come home, and that's what we did. And I'll show you some pictures of what it looked like and how it came out in the end. All right. And again, to give you a little conception of what a repair is, so you know that repair is not trivial. This is a CAD picture of the shuttle, and this is the boom that we use to analyze the. It has the camera system on it that gave us all the data. We would take 2 crew members. That's these 2 little blobs down here. They would be out there with essentially a cock gun, and that's where they would have to go to effect that repair. And this boom is probably about 60 or so feet. This is where it's picked up with the shuttle arm here and reaches out to this location. We've done analysis. It's stable enough. It doesn't bounce up and down. It's a good work platform. But still getting into this location, if you can imagine in the bulky spacesuits, and your feet are probably about 4 inches away from the bottom of the shuttle, any action where you could bump into the bottom of the shuttle could create another damage site that is equal to or larger than the damage site we're trying to repair. So this was another factor that went into the decision. Was not only was the repair not needed from a thermal analysis standpoint, a wind tunnel standpoint, but also the repair location made it extremely problematic to get to that location to do the repair. So that was another factor that went in. But we clearly would go do this if we had to. There's no issue with this. It's just, do you want to do it for fun, just to go under there to try to make something different and not really repair it? And then kind of the bottom line. This is the picture up on orbit, again, that I showed you earlier in the presentation, and this is the picture after return. And there is really no discernible difference between the two. We actually calculated the volume of lost material, and it's the same before and after. We've analyzed the back part of the wall. There was no glassification. Down in here, you'll see some pictures sometimes in color. You can still see that strain isolation pad. It's still red. So that means the temperature in that region on top of that felt material never got greater than 600 degrees Fahrenheit. Our analysis said worst case it could be 1,000 degrees. So we had maybe a 400-degree margin in our analysis, which is very acceptable to us. So again, this data proves to us that our analysis was conservative, the way it should be. It showed that we didn't have to make any problems or any decisions above what we did, and we made the right decision. But that doesn't say we're done. We now got an awesome analysis case. We know exactly what it was like before entry. We know exactly what it's like after entry. So now we can go back with all our computer codes, all our computer simulations, and with the data point of 1 and a little bit of caution, we'll be able to go in and update some of those codes and make sure that they're even better in case we pick up something like this in the future. So with that, that was the end of STS-118. We're currently now down at the launch pad getting ready to launch STS-120. That's scheduled for October 23rd. We just rolled the orbiter over Sunday of this week, and it's hard attached to the external tank. It'll probably roll out to the launch pad this coming Sunday, I believe the 30th or the 1st, and things look on track for STS-120. We've also, in the meantime, understood better where that foam came from on that strut. We made a small modification to the strut, so the next time we're unlikely to lose foam. It turns out we actually lost a little more than foam. We lost some underlying material underneath the foam, but we fixed that, and so we've repaired all that, so we have a better condition to go fly again. So I think that the story here is that the shuttle program is learning. We take the data, we used all the tools we put in place after return to flight. We used them to their utmost. We used all our analysis techniques. We ensured that we were safe to return to flight. We returned safely. We then looked at the problem again on the ground. We were able to make some repairs for the next flight, get those in place, and we're ready to go fly again. So by continuing to stay hungry, in my words, continuing to keep looking forward, to continue to keep learning, we fly safe. It's only when we start thinking this business is easy and we start relaxing our guard and letting down that we get in trouble. So again, it's my pleasure to give you some insight, and hopefully you learned something from this morning that you'll be able to carry back to your own jobs, because each one of you face problems like this. When you're doing a design problem and you go to your boss and you try to explain to him why you want to make a design change, and he tells you, I don't want to do that for budget, cost, and schedule reasons, then you need to dig a little deeper and give him a little more analysis and show him what needs to be done. But again, by working hard and making those risk versus risk decisions, we can all keep flying safe. So again, thank you for your time this morning, and hopefully you learned something.
We have time for a question or two. Would anyone like to ask Bill something?
My name is Dhananjay Khadilkar. I'm from DNA, English newspaper from Bombay. My question is this detailed analysis, all this computer aerodynamics and thermodynamics, wasn't it available during the Space Shuttle Columbia 2003? Wasn't it conducted then?
We understand.
Yeah, and during Columbia, we didn't, first of all, know we had damage because we didn't have the cameras to take pictures. We didn't have the boom to inspect the damage, and we really didn't have the teams as prepared to go do this analysis. So since Columbia, we've added all these additional cameras to keep looking for problems that could occur, and then we've also started some of the analysis. We had some cases already run with particular size damage, so the thermal guys and the thermal analysis didn't have to start from scratch. They had some data to begin with, so we were prepared for this, and that allowed us to do those runs. So I think now that we understand that this is a problem to us, we were extra prepared for this case.
Frank Mooring with Aviation Week. Could you please describe how the upcoming test of this caulk repair technique on the next mission will play into your analysis, both going backwards and forwards?
Okay. The concern, again, with what Frank talked about is on this next shuttle flight, STS-120, we're going to actually go out into the payload bay and we're going to spray this foam material or this caulk material into some cavities and see how it performs. The problem with this material is it expands in the vacuum, and it's very temperature sensitive. It's like bread dough that rises. You know, it starts filling up and expanding in the pan, and it doesn't always get to the same level of rising. So sometimes it over rises and you have to pound it down with a little brush to keep it in the area you've got. Other times it doesn't rise enough. And so the purpose of STS-120 is to refine that technique so we can understand with some assurity how we can apply this material. This material would clearly work for typical damage sites. We would have no problem with it. We've tested it enough to know that it would work in typical damage sites. But in this damage site where we have this double indication, this double hole, we really need to know more how this foam performs and how we can effectively apply it. And that's the purpose of the test that's coming up on STS-120.
Michael Eiden, European Space Agency. It's always difficult to assess statistical improbable events. Now, as part of the risk assessment, have you looked again into some of those events which have not been analyzed so far to see if there are further issues which should be looked at for next flights?
You're exactly right. What we've done now is where I described to you that this foam had to come off and hit the strut and then bounce up and hit the orbiter. We consider that a fairly low probability event. We've now modeled that mathematically, and it's now included in our model, so that's now considered a valid case. The other thing that we learned was not only did we lose some foam that came off that location, but we lost some material underneath, a super lightweight ablator. It's a tar-like material that is a little denser than foam. That came off with the foam as well. So the piece that came off was heavier than our models and our analysis had predicted pre-flight. So we've now factored that in. We're now looking where there's other areas where there's a blader underneath the foam, and if there's a probability it could come off with the foam, we've added that into the model. So you're exactly right. Our challenge as an industry is how do we find these unknown unknowns? How do we get creative enough to keep searching for these things that we don't know could happen? And that's what we need to do as engineers. Even though it's an extremely remote event, the consequences are very high. How do we identify those remote events and somehow protect for them generically? And I think one way we do it is we're prepared to look for them. So we have the cameras on place that we can look for anything that happens. So if it's something that we haven't even anticipated, the cameras are there. We have the laser system to scan the damage. That protects for us. We have 3 or 4 different repair techniques, and we have the ability to stay on board station if we need to. So we've protected for all those unknown unknowns with other things totally separate, other systems. All right. And again, I want to thank you for your attention today, and hopefully you learned something, and hopefully you can apply this to what you do every day. Thanks.